Hello. So another example problem, this time of an elastic collision. In this case, we're actually told it's an elastic collision. In other problems, you might be asked to determine that, but here we're taking that little factor out. Okay, so here's the statement of the problem. A 100-gram air hockey puck moving to the right with a speed of 5 meters per second has a head-on collision with a 150-gram puck, which is initially at rest. Assuming an elastic collision, what will be the speed and direction of each puck after the collision? All right, first, a little diagram is in order. So let's call them number 1 and number 2. And we're told that this one, so the second one's velocity initially is 0 meters per second. It's stationary. And the first one is moving to the right with a speed of 5 meters per second. Okay, we're told the masses of these two things. And we're told to assume an elastic collision and determine the speed and direction of each puck after the collision. So in other words, we want to know after the collision, so if this is just before, what's happening after? So V1F and V2F. Okay, so a couple of things here. You can apply almost immediately one of the special conditions that we've got, right, for elastic collisions. But before we do that, let's think about how we approach this problem. We have two tools to use. One is that the kinetic energy of the system before has to equal the kinetic energy of the system after. That only applies for elastic collisions. And then, of course, we've got conservation of momentum, which applies to all types of collisions. And so those are our two tools. And we can just start from there and we can work all the way through. But we also have one other condition, right, that derives from combining these two, which is that their relative velocities before have to equal the magnitude of their relative velocity after, albeit opposite direction. So if they're approaching to begin with, they're going to be receding from one another to end with. And if we look at that, that is initially very tempting, right? We want to know about the velocities, but we don't know either of the final velocities. So although we know what this is going to be in total, right? It has to be 5 meters per second. Well, negative 5 meters per second, just because the initial relative velocity is 5 meters per second because it's 5 minus 0 over here on the right-hand side, or left-hand side, rather. But it won't tell us specifically what each one of those is. So we're going to need to use at least one other of our tools to determine this. And I'm going to start with momentum because that's relatively easy to write down, no squareds or anything like that. So let's start with momentum. Move over here, and we've got M1 V10 plus 0, right, because the second one is not moving initially. And then we've got V1F, and we've got M2 V2F over here on the right. And I'll leave them little vector symbols to demonstrate that we don't actually know their directions, so one of them might turn out to be negative, okay? And if we just look at that expression, we know everything in it except for the two unknowns that we want, right? We know everything except for this and this. And if we look at this expression, we know everything except for this and this, the same two vector quantities. So the technique here is to use this system of two equations and substitute one into the other to solve for what we want. And it's pretty arbitrary which one we solve for and then substitute for, but I'll pick, let's say V1F, right, is what we want to solve for. And so what I've done is I've added it to both sides and then subtract both of these things over to the other side. So that leaves us with these, and this one stays after we distribute the minus sign through. Okay, So check my math there. Let's see, that should go addition, subtraction, and then this comes over there. Okay, I think this checks out, okay? And if we want to substitute in some numbers there just to make the substituting back and forth a little less cumbersome, remember that this term is just 0, and this term right here is positive 5, but there's a minus sign in our equation here. So we end up with v1 final equals negative 5 plus this, okay? And so, pardon me while I put in some dividing lines here, okay? Okay. So wherever we see a v1 final in our conservation momentum principle, we can substitute this expression, okay? So let's do that. Okay, there we are. So we substituted that across, and now we have everything in terms of a single unknown. We just need to kind of clean things up here a little bit. So we have 5 meters per second times m1. We distribute this onto there, so we have negative 5 m1 plus m1 v2 final, and plus m2 v2 final. And then we can group up terms, so we have 10 m1 once we add this term to both sides, and then we can sum up the masses, factor out the thing that we're looking for, and divide both sides by the sum of the masses, which if we're substituting in, okay, gives us 0.1 for going for kilograms, and 0.1 plus 0.15, and that gives us that the final velocity of the second object after that collision is 1 divided by 0.25, which is 4 meters per second, and it came out positive, so we know that that's to the right. So this should be 4 meters per second to the right, okay? So there's one of our answers, okay? Just to make it explicit, to the right is positive, to the left is negative. All right, and now we can go back to this expression right here to find the other thing that we want. Let me bring that down. So v1 final is negative 5 plus our final velocity for the second object, which gives us a negative 1 meter per second for the other velocity. So here, this thing is moving just a little bit to the left at 1 meter per second. You'll notice that the relative velocity here, if you go back to the original statement of that thing, here we're receding from one another at 5 meters per second, and initially you are approaching at 5 meters per second, relative velocity-wise. So that checks out, and there is our answer. Hope this helps.